Hey everyone, welcome to This Explainer. Have you ever just stopped for a second to wonder about the silent forces governing our reality? Literally every step you take, every physical object you interact with, and even the light hitting your eyes right at this very moment, it's all dictated by strict, hidden rulebooks. Today, we're going to pull back the curtain on these concepts. We'll explore everything from how we move through space to exactly what allows us to see the world around us. Here's the roadmap for our journey. 1. The rules of movement. 2. Elasticity and equilibrium. 3. Electricity and magnetism. And 4. Light and electromagnetic waves. All right, let's jump right into section 1, the rules of movement. This is basically the foundational language of motion. To really get how things move, we've got to split motion into two essential buckets, scalars and vectors. A scalar just tells you how much. Think about distance. If you walk 5 kilometers, that's a scalar. It has magnitude, but no direction. But displacement, that is a vector. If you walk 5 kilometers specifically to the north, boom, you've just given that movement a precise direction in space. It tells us how much and in what direction, which is absolutely crucial for mapping out reality. And when we measure that motion over time, we're really contrasting two different things. Think about a cross-country road trip. Your average velocity is the big picture, your total displacement divided by the total time of your travel. But your instantaneous velocity, that is incredibly specific. It's the exact rate and direction you're moving at 1 frozen millisecond. It's exactly like looking down at your car speedometer at a single exact second on the highway. Moving right along to section 2, elasticity and equilibrium. Let's look at the structural rules of the physical objects around us. Think about a bouncy brass spring, or just the super satisfying click of your pen. These little everyday actions depend entirely on the microscopic structure of materials reacting to applied force. When you press down, you cause a deformation. But the fascinating part is how these specific objects are engineered to perfectly bounce back to their original state the second your thumb is removed. Now, contrast that perfect bounce back with the intense forces of a hammer ripping a nail out of a board. As the hammer pulls, the nail actually experiences static equilibrium, fighting the pull of the wood, but its physical form is just totally overwhelmed. It deforms and stays bent. No bouncing back here. So the crucial takeaway here is the difference between elasticity and plasticity. Elasticity is that invisible superpower, letting our pen clicker snap right back to its original shape and size. Plasticity, on the other hand, means the material permanently yields to the stress. It loses its original form, just like that bent metal nail. The microscopic structure is literally altered forever. Okay, section 3, electricity and magnetism. Time to dive into the truly unseen forces. When we shift from physical objects to invisible fields, it all boils down to some really basic rules of attraction and repulsion. In nature, you've got strictly two types of charges, positive and negative. It's a simple, undeniable cosmic law. Charges with the same sign will aggressively repel each other, pushing away, while charges with opposite signs magnetically attract. And you know when you get a shock from a doorknob? That charging is literally just the physical process of removing or adding these tiny charges to a body. That's the whole mechanism. And just like those electric charges, diverse shapes of magnets generate their own invisible magnetic fields that exert powerful forces. From the classic horseshoes and bars to cylinders and rings, the physical shape might change, but the underlying rule doesn't. And here's where it gets wild. Electricity and magnetism are intimately linked. A moving electric charge actually creates a magnetic field, and these magnets interact right back with those exact same fields. Let's bring it all together with section 4, light and electromagnetic waves. This is all about how we actually perceive the universe. So, how does light physically make its way to our eyes? It's all about the propagation of an electromagnetic wave. It kicks off with electric and magnetic fields oscillating, vibrating together in harmony. This interaction generates a wave that radiates outward from the source. And remarkably, this wave doesn't even need a physical medium. It can zip right through the empty vacuum of space or pass right through solid matter like a glass window. And man, does it zip, 3 times 10 to the 8th meters per second. That incredible number is the speed of light in a vacuum, almost 300 million meters in a single second. It is literally the ultimate speed limit of the universe. But here's a fun fact. This speed actually changes depending on what it travels through. When light hits water or glass, it slows down, proving that even light plays by the physical rules of the medium it's in. Now, when that light finally hits objects, the beautiful colors we see are dictated by strict rules of addition and subtraction. Color addition involves combining the primary colors of light directly to create new, vibrant hues. But color subtraction, which is exactly why a leaf looks green or a car looks red, happens because pigments in those objects act like little filters. They absorb specific colors of light from the spectrum and only reflect the leftover colors back into our eyes. Furthermore, the way those light rays behave is the very reason you can see your reflection in a mirror before leaving for school, or why glasses can correct our vision. The law of reflection dictates how light predictably bounces back off smooth, polished surfaces. Meanwhile, the law of refraction governs how light physically bends as it changes speed, passing from one medium to another, like going from the air into a curved glass lens. As we wrap up this explainer, I want to leave you with a bit of a mind bender about those hidden laws of refraction. Think about a diamond. Will light traveling from a diamond into silicon ever undergo total internal reflection? When light passes from a super dense material like a diamond into another medium, the extreme bending of light can actually trap the rays inside the stone, causing them to bounce off the interior walls. That phenomenon is total internal reflection, and it's the exact reason a precisely cut diamond sparkles so brilliantly. It just goes to show you, even beauty is governed by the invisible rules of everyday reality. Thanks so much for learning with me today.